Hi, I'm Marcin Zabłocki. I'm MLOps architect at GetInData and welcome back to our GetInData YouTube channel. In this tutorial, I will show you how you can combine the worlds of PyTorch and Kedro in one machine learning project. And first of all, you can ask whether it's a good combination at all. And yes, it is. And today I will show you how it can be done while maintaining all of the benefits from the Kedro world and all of the benefits from PyTorch world without any sacrifices and any workarounds whatsoever. So grab a coffee and let's get started. So Kedro and PyTorch. What do we have in both of those frameworks? So first, let's see what are those two frameworks bringing to your machine learning projects. In Kedro, you have abstraction of pipelines and nodes, which allow you to decompose the whole machine learning pipeline into separate and easy to maintain pieces. You have a good abstraction of parameters, which allow you to abstract the configuration of your pipeline into a separate file that can be managed. You have environments, so it's like another layer on top of the parameters and the configuration. You can easily switch, for example, between cloud and local environments with a simple switch. And you have the data catalog, which is a great abstraction that Kedro brings to ML projects, where the data itself is not loaded directly by the user code, but the user code only operates on the data while the framework itself loads it. And from the PyTorch perspective, obviously it's a neural networks library that allows you to train large scale deep learning models. You have support for distributed computing there. You have a lot of data processing and data preprocessing functions that are included in for example, PyTorch Vision library. And obviously you have datasets. And now, as you can see in here, we have slight collision between those two frameworks because the abstraction of dataset on the Kedro side is slightly different than the abstraction of the dataset in PyTorch. However, after watching today's tutorial, you will know what are the differences between those two and how you can actually combine and leverage both of those abstractions in one project. So when it comes to the dataset themselves, let's compare them. So in Kedro, you have the datasets are declarative, so you define them in the data catalog, while in PyTorch usually they are defined in user code, so very often it is that data scientists write the dataset loading code and the only abstraction there is some kind of a paths or slide configuration that points the PyTorch dataset loader into the right direction, for example, on the disk. And when it comes to dataset loading in Kedro, because it's declarative, the framework, which is Kedro here, loads the dataset for you. So when you are executing the nodes, the underlying Kedro runner actually loads your dataset. It calls appropriate APIs. And from the code perspective, when you are executing a node that is a part of your machine learning pipeline, what you are getting is actually the loaded data. For example, if you are loading CSV file, you don't have to call the, for example, pandas read CSV method. You will just get the data frame directly as a object loaded into your memory. While on the PyTorch side, the datasets are loaded lazily, usually in your training loop. There's a data loader that calls the dataset and it loads the data in more lazy manner. And next thing, the pre and post processing. So in Kedro, because actually there is no abstractions for that, you are actually running the Kedro nodes to preprocess any kind of data that you want to do. And in PyTorch, the datasets are usually created and implemented in a way that they are accepting some kind of parameters that allow you to plug in some custom behavior. So to bring you an easy example from computer vision, you have datasets that allow you to load images from disk, and at the same time they are accepting some parameters when you can plug in custom behaviors such as data augmentation or just translating some kind of RGB values, for example, to some other color space. And lastly, dataset saving. So in the Kedro world, the datasets are usually supporting both loading and saving. So nodes can return some data, and when you mark this data in your data catalog, the data will be saved, or at least when you are using the dataset that supports saving, it will be saved. While on the PyTorch side, since we are usually only training neural networks, we're usually only loading the dataset. So the built-in abstraction from PyTorch does not support saving. So besides datasets, there are some other challenges which you can encounter when you are implementing Kedro and PyTorch machine learning projects. So you might ask how to actually save the trained model from PyTorch in order to use it later on further down the Kedro pipeline, and also how to do the inference when you are ready with your trained model. So after watching today's tutorial, you will be able to answer all of those questions, and you will be able to re-implement what I've shown you today in your own project. And don't worry, all of the code will be available at GitHub. So the link will be below this video. So it's time to start coding. So for today's tutorial, I've prepared a simplified version of Stanford cars dataset that instead of predicting a specific car model, it predicts only the brand of this car, just for a simplification. And the dataset is structurized whether on a disk or in some cloud storage, in the standard computer vision way, so that you have folders for both training and testing and so on. And within those folders, there are subfolders that determine the actual class. So as you can see in the slide, we have, for example, training dataset with Acura, Aston, Audi, and so on, and the testing set with the same set of classes. So here you can see PyCharm with the Kedro project already opened. So you can see the standard Kedro structure with source, data, configuration, documentation, and so on. But what's important here is what are the actual pipelines, right? So let me switch to the Kedro visualization for that matter. So here you can see Kedro visualization of my training pipeline. So it trains the model and then saves it to disk. And at the later part, it loads test data and evaluates my model and shows me some metrics. So let's dive deeper. So here you can see that I'm loading testing dataset. I'm splitting the training dataset into further validation and training datasets. I'm also extracting some label information. So I need to label my actual car makes, car brands into some integer numbers, and I need to save this information for later inference. So once I have all of those intermediate data prepared, I'm calling the node to train the classifier. I'm saving the PyTorch model, and on the left-hand side you can see it's simultaneously I'm loading the testing dataset, and then I'm passing the test dataset and the model into my evaluation node. Okay, so let's dive deeper into the actual components of the pipeline. So first we have the listing of training files. So this is the first place when the worlds of Kedro and PyTorch collide because of the different dataset abstractions. So usually from the PyTorch perspective, what you are doing in the image classification problems, you are using the image folder dataset, which allows you to load the dataset from disk. And this dataset is laid out on a disk in the same way that I've shown you on the slides. And when you want to do something similar in Kedro, you have the abstraction of partition dataset. So instead of reading single files, Kedro can actually iterate on some folder automatically. And for each of the file that it encounters that matches some filters, it loads sub datasets to some extent. And in the official Kedro documentation, you can see that here we have partition dataset example with pandas dataset, and that contains the path, parameter, and file name suffix. And what it means from the Kedro perspective, it instructs the framework to go to this path folder, find all of the matches that are all of the files that have a .csv suffix, and then for each of those files, it will create sub-dataset of this partition dataset of type CSV dataset. So what it means is that from the node perspective, you will not get direct reference to in this example, pandas data frame. you will get the reference to the partition dataset and you will actually have to load the data on your own. So this is exactly what I've used here. So let's open the code of this particular node. So as you can see in here, I'm loading each of the partition, which means each of the file that is stored on the disk in my training dataset layout, and I'm appending all of those files to my result array, and then I'm returning the pandas data frame. And what's important here is that what actually this partition data set is. And here is the first implementation of Kedro plus PyTorch that I did in order to combine those worlds together. So let's go to the configuration, and in the data catalog you can see training images list, partition dataset, of type file with directory as label. This is my implementation, and I will go into the actual class in order to show it to you. So what I'm doing here is, instead of actually reading the files into memory, I'm just passing on the metadata. So as you can see in here, I'm returning the dictionary of paths and label comes from the directory name. So this means that for each JPEG file that I have in my data set, I will get its path and the name of the parent folder, which in my case will be the label. So let's go to the pipeline. And here in the list files that I've shown you before in the Kedro visualization, when I call this load function, it will actually return my dictionary. And thanks to that, I will create the data frame that will have two columns, one for path and one for label, that I will be using later on. Okay, that's the first component. Let's go further. So next, I have this split train validation. This is a simple code that does the stratified sampling and splits my training dataset into validation and training components, because Stanford dataset does not have a validation component built in, so I've extracted it from my training set. And the second part is creating this label to index mapping, which basically means creating a dictionary that will have a class name as keys, which are strings, and they will be mapped into integers. So again, here I'm using the data, I am extracting my target column, which will be label in the configuration, and I'm creating this dictionary of string to integer mapping, and I'm returning it. And those two data sets are saved in my data catalog in here. So I have my label to index and also my train dataset here. So the label to index is saving label to index dataset, and split train validation is saving train dataset and validation dataset. And actually here is the second time when the Kedro and PyTorch dataset collide, and actually this one is more interesting. So let's see what happens inside. So as you can see in here in my catalog, I have this train dataset defined, and I've implemented my Kedro PyTorch image dataset. So when I open the implementation, this class actually inherits from two base classes. So one is satisfying all of the things that Kedro wants from the dataset. So I'm implementing the abstract dataset class from Kedro. So when you open it, when you want to implement your own dataset in Kedro, usually you implement those three methods. So you have some method to load your data, some method to save your data, and some method to describe your data, for example, for debugging purposes. So those are the three methods that are implemented by me for the Kedro. And for the dataset, which is here from the actual PyTorch dataset, I have to implement one method or two methods. So get item basically means, hey, please fetch me the item with a specific index from my dataset. Optionally, you can also implement length in order to instruct PyTorch what is the size of your dataset. And this is exactly what I did here. So in the initialization, there are many parameters that you can override. Most of them are related to the way the Kedro loads your dataset. And of course, I am supporting the FS spec. So a lot of the code that you can see in here is related strictly to FS specification. So that means that instead of using standard local paths in here, you can as well use, for example, GCS or AWS S3 or Azure Blob Storages in here in order to save and operate with your data. And then I have the implementation of Kedro load and save. So as you can see, loading my dataset from the Kedro perspective means basically loading the CSV file from disk. So that CSV file contains the paths and labels of my files that we'll be using when I will be training my neural network. And the save method here uses fsspec to load the actual data into memory. And here, the load and save methods, you can treat them as they are loading only the metadata for my training dataset. I am not loading my images directly into the memory yet, because this is the thing that actually PyTorch will do. But what's important in here is that from the load method, I am returning self. So what it means that after I load the metadata of my training set or testing set, I will return this particular class, which is indeed the PyTorch dataset. So then all of the nodes that are expecting something related to PyTorch and dataset that are PyTorch datasets will get the actual PyTorch dataset. Okay. And when it comes to the implementation from the perspective of PyTorch, I have this getItem, which actually uses the fsspec again, with the twist that it, for the given index, it looks up into this internal data frame for my both path column and label columns. And for the PyTorch implementation of dataset, I have this getItem and length functions. So in the getItem, I'm using this internal data frame in order to fetch the path of my image and also its label. And I'm passing those two information into transform and target transform functions that are within this dataset. And what are those transform? PyTorch users will be familiar with those. So let me go back again to this image folder. It contains the same classes. So we have transform and target transform. Those are optional callables. So it means that you can pass any function to this argument. And what it will do, it before returning the data from the getItem, it will call the transform function on the image and target transform on the label. So in here, for example, I will use it to transform my dataset, to augment my dataset, to resize my images, and target transform will be used to map the class name, so string, for example, BMW, Audi, and so on, into the integer. So last thing is the with transforms utility function, which actually binds together the Kedro nodes with my PyTorch dataset. Thanks to that, I will be able to pass my custom transformation and target transformations into the dataset. So whenever PyTorch calls getItem, it will call the transform and target transform methods. Okay, and let's go back to the Kedro visualization. So we have all of the dataset related parts already together. And the last thing here is to train the classifier. So let me go back to the pipeline. Here I have my train PyTorch model function. So in here I am using PyTorch Lightning in order to simplify my PyTorch code implementation. But from the Kedro perspective, we have this train dataset and validation datasets, which are instances of my Kedro PyTorch image datasets that I've just described. I'm also taking the label to index dictionary and the parameters. So now let's go to the actual parameters. So from the model perspective, I'm using the backbone parameter, the learning rate, epochs, batch size, and image size and max steps. So those are the standard deep learning parameters that you would probably need in your machine learning, in your deep learning projects. You can obviously customize it or make some nested structures here to fit your needs. Okay, so I'm constructing my image classifier. I'm passing the backbone from the parameters. So those are remember Kedro parameters. I'm passing number of classes, which will be the length of my mapping and the learning rate. So inside, this is the Lightning module that downloads my backbone model from Torch image models. I have the loss that will be cross entropy loss, and I'm also tracing some metrics. In here, I will be tracking multi-class accuracy for training, testing, validation sets. And the implementation is standard PyTorch Lightning implementation of any Lightning module. So I will not dig deeper into that. You just need to see that the forward function from the standard PyTorch is calling my model with the normalization, and the normalization will extract the mean and standardize my input ImageNet compatible ranges, since I'm using pre-trained model that was trained on the ImageNet. Okay, and here I'm constructing my trainer from PyTorch Lightning. So again, I'm passing the parameters and the epochs from the Kedro parameters. I'm passing the max steps, which will be by default unlimited. And I'm optionally using GPU if it's available. On my local machine, I don't have a GPU, but I will show you that you can easily add a new environment to Kedro and run it in the cloud. So the same project will run with GPU. And I'm calling the fit, and here is the place where I'm combining the worlds of Kedro dataset and PyTorch dataset. So up to this point, I had this train dataset, which was only the Kedro thing, but I'm calling the with transform method here. So this is where I pass the Torch vision transforms. So I'm doing data augmentation. I'm resizing it to my given image size, and I'm transforming the images to tensors. And the target transform is the function that takes my label to index and maps it to the integer tensor, so that I will be able to use cross entropy loss. And I do the same for the validation data loader. And once the fit method is executed, my model will obviously train for the number of epochs or number of steps based on the parameters from Kedro. Once it's done, I need to save the model. So again, I need to go back from PyTorch world into Kedro world into the data catalog. So in order to provide the maximal compatibility between training and serving of PyTorch models, I'm using Torch script. So I'm transforming my Python class with the model into scriptable version of PyTorch, so that later on, when I, for example, use the model in the inference, I will not have to have my Python class definition of my model structure. I will just have one binary file that I will be able to load with just a PyTorch as a dependency. And this model, when we go back here, will be saved. And this is the last place when I'm implementing something for Kedro related to PyTorch. So if we go to the catalog, you will see that in the model, I have another custom dataset, which is a Torch script model dataset. And when we go to the implementation, again, this is some boilerplate to handle FS spec, but the meat is here. So the load function just loads the model into the specific location. By default, it's a CPU mentioned here. TorchJIT will load my Torch script model, and when I'm saving that, so that happens after training, I'm using fspec to save my model into the specific file system. Okay, and the last thing here, we have the evaluate model. So in this function, so here again we are combining the worlds of Kedro and PyTorch. So any Kedro node can be marked with Torch node grad decorator, which means that I will be disabling gradient tracking for Kedro because I'm doing only inference. And the evaluate function, evaluate node takes the model as a parameter. Here it's no more the image classifier that was used in training. It's just a script module from pure Torch. So the model is portable. Again, I have test dataset, label to index mapping and parameters. I'm doing the same magic with transforms in order to create my data loader. Here, this is a pure PyTorch, so I'm checking whether GPU is available, and I'm passing this device parameter to my data. And with standard Python loop, I'm going through my test data set and I'm tracing all of the metrics that I want to. And here I have precision recall and accuracy from torch metrics package. And at the very end, I'm just putting them to standard output. Okay, so when you're working with PyTorch and Kedro, the best thing to do is to always have some kind of parameters that allow you to quickly run through the whole pipeline without waiting for the actual model to train. So in my base configuration, as you might see earlier, I have my epochs specified to 3, but I also specified max steps to 32. And I've also added limit test set parameter in order to limit my test data set to 100 examples, so that when I execute this pipeline locally on my machine without GPU, it will only take a minute or so to run through the whole pipeline. And thanks to that, I will be able to spot logical errors in my pipeline at really fast pace. Okay, and the pipeline is executing right now on my local machine. It takes a few seconds, but after 32 steps, it will finish and it will save the model and proceed to the evaluation part. Yep, it's happening, and as you can see, the metrics are garbage, but the pipeline has finished, so at least from the logical perspective, I can see that my pipeline is working. So right now, I'm able to proceed with my project and try to train the actual larger model. So I will switch the configuration here to my cloud configuration, and as you can see in here in my environments configuration, I have the cloud configurations. So when we compare them side by side, you can see that I've changed the backbone to a slightly larger model, and I've also I'm using larger images, larger batch size, thanks to the GPUs, and I'm also skipping the limitation of maximum number of steps. So we'll try for the whole 3 epochs on GPU in the cloud. And obviously in the data catalog, I've changed the parameters so that they are pointed to the dataset that I have stored on my remote machine that I'm connecting to it right now. So when I run it again in the cloud configuration, it will connect to the cloud VM with GPU and it will train for the all 3 epochs. So okay, now evaluation is about to finish and you'll see the actual metrics of the trained model. As you can see in here, model trained for 3 epochs gave us accuracy and precision of about 74-76%. Okay, now that the model is trained, we can use it for the inference. And again, in order to use it in a Kedro way, I implemented one simple pipeline that consists only one node that has a predict node, which takes the model as a parameter labeled to index mapping that we've seen before, and the parameter which will be the file. And if we go deeper into the implementation, you can see that I am again calling the node gradient decorator from PyTorch, and I'm passing my model again through PyTorch script model labeled to index and file. I'm opening this file, resizing it for the sake of performance. I'm transforming it to tensor, and I'm calling my model and then applying softmax in order to retrieve the probabilities of each class. And for the probabilities that are relevant, I'm printing the level of the probability and the final prediction. So that's how you can, for example, run your prediction on a single file. You can as well transform it into some loop in order to go through your folders for the inference in Kedro. Okay, so let's run it. I've prepared a few files for the inference pipeline testing. So I have one image of Aston Martin, one image of Lamborghini, and one image of Alfa Romeo. So what we need to do is to just call Kedro run -d means pipeline I'm using inference pipeline defined in my inference pipeline in here. And I'm passing one parameter, which will be the file, which will be the direct path to my image. And Alfa Romeos were not in the actual training dataset. So as you can see, the probabilities are all over the place. There are many cars that might be predicted here because the Alfa Romeos were not in the training dataset, unfortunately. But when we go, for example, for Lamborghini, and we'll run the pipeline again, after a few seconds, we should see that indeed, because Lamborghini was in the training dataset, we can see clearly that it is indeed recognized as our target class. So that's all of the things that you will probably need in order to run your machine learning projects with Kedro and PyTorch. A few things to remember. First, use the Kedro datasets abstraction whenever it's possible. It's a great piece of abstraction that simplifies the way that machine learning pipelines can be implemented. Next, try to not reinvent the wheel, so try to leverage all of the functionality that both frameworks have to offer. For example, you can combine PyTorch and Kedro datasets in one place. You can annotate Kedro nodes with PyTorch decorators and so on. So try to always come up with the solutions that benefit from both worlds instead of writing something from scratch by yourself. And always remember to add some parameters and leverage Kedro environments in order to make your development look much faster and focus on the logical perspective of the pipelines themselves instead of trying to train the best models first. And if you want to push your Kedro plus PyTorch projects to the next level and train really huge neural networks in a distributed manner, I encourage you to check out the link in the video description when I show how to use distributed training in Azure ML with the obviously combination of Kedro and PyTorch. Thank you for your time. I hope you liked this video. Please give us a thumbs up and subscribe to our channel for more videos like this one in the future. Bye!